All right, this is going to be the video for chapter 23 in AP Statistics, which is our first chapter of Unit 6, Inference using numerical data where we can calculate a mean. So we'll start by looking at the notes here. The first thing we're going to have you do is, typically if we're in class, is I have people work on a problem and try to come up with a solution, usually in groups if we're able to group up. And it's just the first page of the required practice packet. So if you were to look at that with me here in a second, I'm going to pause the video, but I'll display the problems so you can work on them. These are the problems right here. And this is something that you might want to know about while you're working it. So the first question is a speed limit problem. It says the speeds of cars on a small road with a speed limit of 30 miles per hour were monitored. The following speeds were observed, and there's a small data set here. Use a hypothesis test to determine whether or not the average speed of all vehicles on this road exceeds the speed limit. And then separately, we also want to use this sample to build a 90% confidence interval for the average speed of all vehicles traveling on the road and then interpret that interval. So you can go ahead and pause the video here and then attempt this problem using what you know right now. Just do the best you can to try to solve the problem right now. And you can write it right into your practice packet. Okay, so assuming that you've had a chance to try this, I'm going to go ahead and show what people usually do when they solve this. And it would look like this. So first of all, we would say, I need a hypothesis test, so I'm going to define a symbol here. Now, this is numerical data, so I don't have yes or no percentages. So instead of using like a p, I'm going to use the mean symbol mu when I do my hypotheses. And usually people will think about that and think, okay, instead of a p, I have a mean. I have a standard deviation too, but this is asking me about whether or not the average speed exceeds the speed limit. So it's going to be about the average. So let's define this as the average speed of all cars on this road. We'll use the symbol mu for that. And that means our null hypothesis would be that that mean is equal to the kind of, okay, nothing to see here value, which would be the speed limit that's given, 30 miles per hour. And we could write that out in words too, right? The average speed is 30 miles per hour, okay? So then the alternate hypothesis would be something noteworthy, right? We want to know whether or not it exceeds the speed limit. So since this is exceeds, we would use the same numbers here, right? Miles per hour, but we would use the greater than. So the average speed is greater than 30 miles per hour, meaning that the average car is speeding, okay? And then we would check the conditions. Now, hopefully you thought to check the conditions, and maybe you thought SRS, right? Do we have a random sample of cars? It doesn't really say, so let's assume these cars are typical that we observed. We usually have to have an independence thing, seems right. Okay, so we can assume there's no connection between the cars. Cars are not connected in some way. There's not like they're in a caravan or something like that where they're all going the same speed. And then in the last unit, we had, N is less than 10% of the population. So let's put that in there. 30 is less than 10% of all cars on the road. Seems like that might be on this road. That seems likely. Okay. And then there used to be an NP and an NQ, but we don't have a P anymore. So maybe we would revert to the chapter 18 idea that the sample size is at least 30. Okay. And it is, right? 30 is greater than or equal to 30. So that means that we'd have a normal curve at the sampling distribution model level. So that seems like a good thing to do for checking conditions. All right. So then that means we're going to have some value in our that corresponds to the p hat, right, where we calculated the percentage. But now that's not a percentage anymore. Now we're talking about the average, right? So since I have data here, I'm going to actually have to resort to using a calculator to find the statistic, right? Because the statistic would be the average speed in the sample. So what I would need to do is go stat, edit, and then enter this data in. So we can enter 29, 29, 24, 34, 32, 36, 28, 31, 31, and 27. And then we could run one variable statistics on that data list to get the average is 30.1. Okay, so while we're at it, let's record also the standard deviation in the sample. The standard deviation is the sample standard deviation here, which is 3.4785 because this is a sample. All right, and then if we were thinking, okay, usually we're going to take the statistic, which is in the center, which is this, and we're going to have a sampling distribution, right? So we'll have a sampling distribution that we calculate. So we have some value in the middle, and that's going to align itself with the null hypothesis value, which is 30. So we would put 30 here to see how x bars vary. But we have to have something for the standard deviation, the standard error for means, right? So instead of using the square root of PQ over N, we might have to switch to the chapter 18 formula standard deviation over square root of N. So again, I don't have the values from the population, but I do have this should have been labeled S. I do have the values from the sample. So I could compute what the standard error is by using the value for the sample. Standard deviation was 3.4785 divided by the square root of the sample size. So when you compute that, you get 1.1. And this has units now because it's numerical miles per hour. So most 68% of cars would be going within about a mile per hour of the speed limit. Looks like above or below, if the null hypothesis assumption is true that these cars are averaging right at the speed limit. And then we have our particular boundary value, which was 30.1, which is maybe about here, 30.1. That's the actual x bar in the sample. And so then we could shade to the right, and then use a normal CDF function to compute the p-value here. So the p-value would be normal CDF from 30.1 to infinity if the mean was 30 and the standard deviation was 1.1, labeled lower upper mean standard deviation. So we do that in a calculator and we end up getting 0.4638. And then we write up our analysis paragraph at the end, the conclusion paragraph. The first sentence would be something like with significance level of 0.05, p-value equal 0.4638 is high, much higher than 0.05. So we fail to reject the null hypothesis. That would be the first sentence. And then the second sentence would be the conclusion based on the wording for the alternate hypothesis. So if we didn't reject the null, then we do not have sufficient statistical evidence to conclude that the alternate, that the average speed of cars on this road is greater than 30 miles per hour, right? In our sample, we did have something that was a little higher than 30 miles per hour, but it wasn't high enough to say that we believe that all cars would be averaging greater than 30 miles per hour. All right. So if you did that, that's fantastic. That means that you were able to apply the ideas from Unit 5 and just switch over to a new data type where we had to use a different statistic, which was the mean. And then if we did the second part of it, we might say, okay, to build the 90% confidence interval, well, when we had the single sample version from the last unit, it was p hat plus or minus c star times the standard error of p hats. So it makes sense that now it would be the mean in our sample plus or minus c star times the standard error of the means. And in fact, that's what it is. So if our average was 30.1 miles per hour in the sample, and we want 90% confidence, maybe we do a little thing over here on the side for z-scores and put 90% in the middle, 10% left over, which is split 5 and 5, and then find the z-star with an inverse norm calculation. So 0.05 below 0.1, which turns out to be 1.645 or 1.64. So 1.645, I'll use that number, times the standard deviation there, which we calculated here using the sample value, right? And we got 1.1. So if we want 1.648 standard deviations that are each this big above and below 30.1, we would get 28.29 as the lower bound and 31.91 miles per hour is the upper bound. And so then we would finish with our sentence that's like this. We would say we are 90% confident that the mean speed of all vehicles on this road is between 28.3 miles per hour and 31.9 miles per hour. Right. So if you did that, I mean, bravo, that is perfect. That's exactly right. It just meant that you could see how we could just change over to a new data type and then do this exactly like we would before with just some slight variations. And that's essentially correct in what we're going to do in chapter 23. But I think I mentioned this before, that when we switch to data types other than proportions, there's going to be some caveats and some twists and some extra little gotchas that come along the way. And so while this seems correct, it's actually slightly wrong. And there's no way you would have had to know that. It just, there's something that you didn't know about yet. So what we did here is almost right, but there's a problem. Okay, so to investigate the problem, I'm going to show you something from using a website. You can also follow along with your on your phone if you want. But to start with, let's, instead of treating this problem as a numerical problem, let's treat it as a categorical thing, because we could just divide the cars that are in the sample on the road into, are they speeding or not, right? In other words, we could turn this into a proportions problem by saying, let's just count the number of cars going over 30 miles per hour. So if you go back in the sample, we can do that, right? Because when we look at the sample, it looks like 1, 2, 3, 4, 5 of the cars are going over 30 miles an hour. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So exactly half the cars are speeding. So that would be a p hat value, 5 out of 10.5. But that's just one of many possible samples. So if we wanted to, we could do a confidence interval for that using the unit 6 technique. So 0.5 plus or minus the 90% z-star value times square root of 0.5 times 0.5 over the sample size. And that would give us that the real value is somewhere between 24% and 76% of the cars are speeding. We're 90% sure that somewhere between 24% and 76% of the cars are speeding, right? So we could think of that, and I want to show you that so there's a website here called www.rossmann/applets/confsim.html. It stands for confidence simulations. Okay, so I've got this actually on open over here too, so I'm going to show you here on the side. And what we're going to do is we're going to replicate that proportions calculation that we just did, because we're more familiar with that. So if I set this, and if you're doing this with me in your phone, you're welcome to do this too. You can set this to proportions, binomial, walled, and then set this pi, it represents what we call P, the population proportion. So this is saying, let's assume that somehow we knew that 60% of the cars on the road are speeding, and let's take them 10 at a time, or a sample of 10, and let's just do this one time and compute a confidence interval with 90% confidence. So if I click sample, it'll put a little dot on the screen, which is my p hat. And it'll be green if it happens to include what the real population value is, which I said was 60%. Okay. You might have red if I do this again. Occasionally I'll get one where the p-hat's further away. And then I would get a red interval because it failed to capture that, right? And if I were to do 100 intervals, so I'll just type the interval 100 and click sample. So I do 100 p-hats, separate samples of 10 cars, and then find out what percentage are speeding. Then if the true value is 60%, and we did a 90% confidence interval, about 90% of these confidence intervals should capture that value. And in fact, they do. This has got a running total here that shows that it's actually in our simulation here, 90.2, which is very close. Okay, so what we're going to do is now, instead of doing this with proportions, let's go back to thinking about this as numerical values. Okay, so we can use the same thing here to evaluate a numerical thing. Instead of proportions, we change this box here to means. We'll use normal here. We'll leave this set at its default z with sigma. And then let's enter a population mean, which means the actual average speed of all cars on this road. Let's assume somehow we knew it was 32 miles per hour. So we'll put 32 in there, and we'll change the sigma to 5. So that means that the cars on this road are averaging in reality 32 miles an hour with a standard deviation of 5. Let's take a sample of 10 of those, and I'll change the interval back to 1. And again, let's set the confidence level to 90% and click sample. So that will compute a confidence interval like we just did. In other words, this corresponds to what we did here to compute our confidence interval in part B. We have a confidence interval. This is one that was calculated assuming some sample that was taken randomly from a population that's centered at 32 miles per hour. All right, and it would be green if it captures the real value, right? And if I do that again, I'm going to get a different value. So this really represents an X bar, an average of 10 cars, what their average speed is. And if I were to do that over and over again, in fact, if I were to do that 100 times, I could see that, in fact, a lot of those values are capturing the interval, the true population value, but some of them miss because they just have to be unusually small, slow cars or unusually fast cars. Right. But if I look at the percentage of these confidence intervals that capture the true value, it's very close to the 90% that we set for our confidence interval. Okay. But the problem with this is that we set this default to z with sigma. And that means that when we calculated the test statistic for these things, when it calculated it, it assumed that we actually used this value for 5 for the standard deviation. In other words, it assumed that we knew the population's standard deviation, which typically we would not know that, right? Normally we don't know that or the actual mean, right? So what we can do is say that's not realistic. We actually would not know the true population mean or the standard deviation. So we have to have some sort of assumption for the mean. So we're going to leave that there. But we can change this to calculating the standard deviation for the confidence interval from using the sample standard deviation instead of sigma. And so if you go to this third box here and you click Z with S, then what it'll do is it will use a normal distribution, right, to calculate this like we normally would, but it's going to use more realistically the sample standard deviation. So now let me just reset the whole thing, and then let's do 100 intervals of that. Okay, now when I do that, the first thing I want you to notice is that the width of these bars, unlike in the previous value, because the width is depending upon going a number of standard deviations, and those standard deviations are calculated with 5, those were all equal width. In fact, let me go back to that for a second. If we do that, notice that all these confidence intervals are the same width because they're calculated using this 5 right here. Right? But if I switch to calculating with the sample standard deviation, then the bar width changes. I have some really narrow bars like this, and I have some really, really big bars. And that's because if I happen to get a sample whose standard deviation is really high, it's going to result in a much less precise confidence interval. It's going to vary around with the standard deviation in the sample itself. right? And the thing that's really disconcerting is if you were to take 100 of these, it's no longer true that about 90% of these capture the true value. In fact, it's down to around 84 or 85%, right? So why is that happening? Well, this is the problem. The problem that the twist that happens with numerical data. This doesn't happen with the proportions problems, but this problem does happen with numerical data. So let's take a quick look at why this is happening. Okay. So the reason this is happening is because when we did proportions over here, right, we always have to calculate this standard deviation, right? We would like to calculate it this way using the actual p, right, from the population, right, which we don't know. We don't know that, right? So instead, we go ahead and use p hat, right? But p hat is a pretty good estimate of p because the p hats always coalesce around p, right? And that's the reason why this is a normal distribution and this is a pretty good estimate, right? So that's why our confidence intervals work out so well. But what happens over here is the formula for standard deviation here, it would be nice if I could use sigma, which I don't know. So I have to switch to the standard error and use S, but S is not the value that's coalescing around the population, right? That's the X bar. X bars are coalescing around the real mean mu, but the standard deviation of the sample is only loosely tied to this standard deviation up here. It is true that if you have more standard deviation in the population, whenever you take any sample from it, there'll be more standard deviation here, but there's not a one-to-one kind of correlation there, right? It's a much looser connection. That's the problem. That's the reason why we see this problem for means, but not for proportions, because means use a calculation for standard deviation where the sample is not a good estimate, not a very good estimate of the population value. Okay, so that's the cause of the problem. So this was first investigated by a man named William S. Gossett, who happened to be analyzing this because he was the quality control engineer at the Guinness Brewery that brews beer in Dublin, Ireland. Right? They're very tightly control the process for brewing beer, and we're talking about now back in the early 1900s when this was investigated. It's a very interesting story. If you happen to have our textbook checked out, it's discussed in the textbook. But this quality control engineer, William Gossett, realized that things were amiss when he measured numerical values versus percentage calculations. There was more variation than would be expected. So he did a lot of simulations, and this was prior to computers being available. So he had to do all this stuff by hand with calculations, just over and over again, trying different random samples and seeing what happened. So he discovered that when you do samples from if you try to build a sampling distribution for a sample mean, the average of lots and lots of different means taken from a population randomly, right? You do get a sampling distribution here at the third level that is symmetrical and roughly bell-shaped, but it doesn't match a normal curve. It's not quite a normal curve, right? This blue curve here is a normal curve, okay? But this red curve represents what happens when you actually look at the sampling distribution model levels for sample means. He found that there was less cases that happened around the middle and more cases at the extremes. There was more probability in the tails of the distribution. So at first, actually, interestingly, he wanted to publish this result because he realized this would be very valuable, not just for brewing beer, and he wanted to write a paper and present it in a mathematical journal. But the people at the Guinness beer company said, no, you can't do that because this is a trade secret now for us. So he just pestered him, and finally they relented and allowed him to publish. But they said, you have to publish it not mentioning where your data came from. You can't mention the name of our company or that it's related to beer processing. So he just not very imaginative guy. Instead of publishing it under his name, he just called himself student, and he published it as if he were a student. So this distribution is called Gossett's student T distribution now, or just a student T distribution, or right now we just call it a T distribution. I'm not exactly sure why it's called a t-distribution. I suspect it might have to do with something about the fact that there's more chances, more likely to have values in the tails. So it might be that the t stands for tails, but I'm not sure. Anyway, this altered version of a symmetrical distribution that's not quite normally shaped, it's called a t-distribution. And that's actually what we use at this third level. So when we do proportions problems, we know at the third level we have a normal distribution as long as conditions for inference are met. What we're going to find now is if we're dealing with means, where we have numerical data, then even when conditions are met, this curve is not normally shaped. It's the shape of a t-distribution. Okay, and we will get the answer correct as long as we just switch to using this other shape distribution. But there's a twist. This t-distribution, actually, there's an entire family of t-distributions, because what Gossett discovered was that the lower the sample size, the more that shape deviated from a normal distribution. So in fact, you have to take sample size into account. The way we do it is we talk about something called degrees of freedom. Okay, so let me see if I can kind of give you an intuitive understanding of what that is. It's related to the reason why way back in the early part of the course, when we talked about the formula for the sample standard deviation, we said that you take first the variance, you take the distance from that each data value is from the mean squared, sum it up, and then you average it by dividing by the number of elements and then take the square root to convert variance back to standard deviation. But we divide by n minus 1 instead of n. Why is that happening? Well, the reason is because let's say you had like some pieces of data here and they're varying like this, right? And then I have another piece of data here. If I have calculated the mean of that data, and then I'm using that mean in the calculation of the standard deviation, then it's okay for this one to vary and this one to vary and this and this and this and this. But when I get to the last one, that one actually cannot vary, because if it were to vary, it would mean that my mean that I was using all along was wrong. So if there's n pieces of data, actually only n minus 1 piece of data are free to move. They're free to vary, right? These are free to vary. So what we say the degrees of freedom is one less than the sample size. Right. So when we pick which curve we're going to use, which t-distribution we're going to use this measurement degrees of freedom. And for this kind of data, for a single sample of numerical data, the degrees of freedom is one less than the sample size. When we talk about things in the next unit and later in this unit, we're going to find that that degrees of freedom sometimes is different than this. But for right now, it's one less than the sample size. All right. So here's the kind of the summary, right? Whenever we have proportions, we use a normal distribution when we calculate things like the p-value, right? And you can think of the boundary value, that p hat, as being, you can convert it to a test statistic using a z-score. That's why everything is called z interval or z test in the calculator, right? And if you have means, you could actually continue to use a normal distribution and z-scores if you knew the standard deviation of the population, but that almost never happens, so we never do that. Instead, we don't know that. We have to use the sample standard deviation to calculate the standard deviation of the sampling distribution model, and therefore we use a t-distribution with some degrees of freedom, which is one less than the sample size. And then the thing that corresponds to a z-score is called a t-value. So if you take the mean and you subtract the mean of the means and divide by the standard deviation computed with the sample, then that represents the number of standard deviations away you are from the middle, just like a z-score. But it's called a t-score, or our book calls it a t-value. All right. So let me just quickly go through the rest of the notes here, and then we're going to finish by reworking the problem we just did, but this time doing it correctly with the t-distribution. I'll show you how it works. So first of all, if you're doing an inference test, so you're doing a hypothesis test, you state the hypotheses, and you switch to using the mean symbol equals some number. And then the second, the alternate one is either less than, greater, or not equal. We have conditions to be met, and we have that we have to have the sample sizes, or it's an SRS that the sample is representative or a random sample. We do in fact have the n is less than 10% population, Technically, there is no independence one for this one, so we don't have to check for independence. But the sample size where we guessed that it was n is greater than or equal to 30, that's only part of the story. The real story is that the sample itself has to be what we call nearly normal. That means that it has to be roughly mound-shaped and have no outliers, okay? And we typically use a histogram to check that. So we'll show how that's done in a second. So then we figure out our sample size, our statistic. We usually have to plug data into a calculator to find that. We find our estimated third level sampling distribution model standard error from taking the sample standard deviation and divided by the square root of n. And then we go ahead and calculate the t-score, right? We take the value minus the null hypothesis value over the standard deviation to find the number of standard deviations away we are away from the null hypothesis. And then when we calculate our p-value, instead of using the normal CDF function, our calculator has a t-CDF function that we can use. The reason why we always have to calculate a t-score is because when we had normal CDF, right? When we had normal CDF, we could enter a lower and an upper bound, and we could enter a mean and a standard deviation, right? Because there was no degrees of freedom. But the TCDF function, because it has to embed many, many, many curves, we have to specify the degrees of freedom, they no longer allow us to enter a mean and a standard deviation. So we always have to have 0 and 1, the default. And that means that we always have to compute the z-score. In this case, it's called a t-score. So we enter the lower bound and the upper bound and the degrees of freedom. Okay. And then we do the same thing with the decision and stating the conclusion. We decide whether to reject the null hypothesis based on the p-value, and then we discuss the conclusion in terms of the alternate. So they're almost the same as what we just did in our guess. A couple of little changes, and we'll go through an example of that. Confidence intervals work similarly. You select a confidence level, find the z-star value that goes according to that, except that this time it would be called a t-star value, which means we have to use an inverse t function to find it, okay? And then we verify the conditions. They're the same as for a hypothesis test. Calculate this. We determine this value. And that t-star value depends upon degrees of freedom because we have to select which t distribution we're using. So we could either use inverse norm or you can use a table. There's a table where we can do that. We're going to use the inverse t method here, and I'm going to assume you have that in your calculator. If you don't, later in the class, I can, or come to tutoring and I can show you how to use the table. And then we calculate the confidence interval the way we normally would, okay? As you might expect, there are calculator functions. There's one called t-interval, and they don't bother to write one sample t-interval or one mean t-interval. It's just t-interval. And then for the confidence interval, it's called a t-test, and you enter the information. We'll go through an example of that. And then I just wanted to mention how we check that nearly normal condition. So we have the population level, right? Maybe it's skewed, possibly, right? We take our sample. The sample may be nearly normal, even if we're sampling from a population that isn't normal. That's okay. So the nearly normal condition has to do with this level, that the sample itself, the data we have, looks nearly normal. So if you're lucky and the sample size is over 40, then you can just assume that this is nearly normal, okay? If it's between 15 and 40, then you use a histogram because then there's enough data for you to see if the shape is mound-shaped and there's no visible outliers. If it's less than 15, then the idea is you want the envelope to be nearly normal, even if this is sparsely filled in. So you're required to check a histogram, but also use a normal probability plot, which we'll do an example of that too. And if you think there's outliers, you can use the box plot to see if it shows you any outliers out here, because you want to make sure there's no outliers and that it's nearly normal, right? At the sampling distribution model level, what's happening is it is true that as long as the sample size is at least 30, the central limit theorem will say that this is approximately normal, right? But the truth is we're going to use a t distribution at this level whenever we have numerical data, right? So the nearly normal check is about this level, the sample level, right? And as long as that's okay, then we can use a t distribution of appropriate degrees of freedom at this level. All right. And then this is just in your notes if you need a reminder of the steps to do a histogram or a normal probability plot. Okay, so that wraps up the notes. But I think to tie it all together, we need to redo that problem we just did, but this time go through all the steps to do it properly. So if you switch back to your required practice packet, the second page will say, okay, we're going to redo the first problem, but this time we're going to use the t distribution instead of the normal z distribution. Okay, so let's go through the whole thing. We would start with defining a symbol, right? The mu is going to mean the average speed of all cars on this road, right? And then HO is going to be that the mean is equal to the historic value of 30 miles per hour. The average speed is 30 miles per hour. And the alternate will be that the average is something greater because it says we want to check if it exceeds. So greater than 30 miles per hour, shading to the right, one-sided upper tail test. Average speed is greater than 30 miles per hour. Okay. Then we would check conditions. Now we know the correct way to check conditions. So let's go ahead and write that properly. We should check SRS, right? Do we have a simple random sample? No, we just have 10 cars that were observed on the road. So we're going to say no, but assume these cars are typical. Okay. And then we don't really have an independence one, but we do have to do n is less than 10% of the population. Okay, so for that, we're going to say 30 is less than 10% of all cars that drive on this road. Okay, so those are met. And now we've got the nearly normal conditions. So now this is the new thing. How do we check if this is nearly normal? So if we have the data, well, first of all, we can look at the data. If this sample size was 40, then we could just say it's nearly normal because the sample size is large enough. But here we have a sample size of 10, right? The sample size is only 10, which means we're going to have to look at both a histogram and we're also going to have to look at a normal probability plot. So let me show you how that works in the calculator. We would enter the data like we did into the list one. So the data is entered. And then we could go ahead and write out do one variable stats to get the mean and standard deviation of the sample. Let's go ahead and do that right now. So the mean in the sample is 30.1 miles per hour. And the standard deviation is the sample one, S, 3.4785. You can only use the sigma if you know this is all possible cars that could ever be on the road representing the population. That's not true. We know we have a sample. All right, so now that that's there, what we're going to do is we're going to plot a histogram. So this goes back a ways, but you go second y equals, go into the statistics plot menu and turn it on, set it to a histogram, which is the third icon. And then you quit out of that second mode and do zoom 9 to display that. And so what we'll do is we will literally sketch what we see as the condition. So I'll just make a little rough sketch of what I see. Okay. Now we want that to be roughly symmetrical. I would say that looks a little skewed right. Slightly skewed right. Okay, so if you think there's a possible problem, or if you see any gaps, which could definitely happen with a small data set like this, then we're required to do what's called a normal probability plot. So the way that looks is we'll go back to the statistics plot menu, go in there, and we'll select the sixth icon over. Okay, and then what we get is something that looks like this. So the normal probability plot, let me label it because this one's not obvious what it is. It shows the z-score of the data in a perfect normal distribution versus z-score in the data. And what you want to see is that this is roughly linear, which it is. So this is definitely good. And that means that this data is nearly normal, the fact that this is linear. If we felt that there was any gaps, like something stood out here where we might think outliers, The way we would check for an outlier is to have the calculator use the IQR rules. If you go back in here and do a box and whisker plot and select the fourth icon, the one with the dots, then it'll separate out anything which is an outlier according to the IQR rules. So if you wanted to just show that you checked for outliers, you could show a box and whisker diagram with no separate dots here. So there are no outliers. Okay, so here's how we check conditions. This nearly normal thing is a little different because now what we do is provide one or more sketches depending on what we see. I think if I saw this, I would definitely follow up with an NPP. Probably don't need to include this because there's no obvious outliers, but if there was any possibility of outliers, I would include the dot plot as well. So that meets conditions for inference. Okay, now that we have that, we can calculate the standard error for the means. Okay, and so that's going to be S over the square root of n. So it's 30.1 in the sample divided by the square root of 10, right, which turns out to be 1.1. Not 30.1, sorry, it's the standard deviation number. It's the 3.4785 divided by square root of 10 is the 1.1 number. Okay. And so let's go ahead right while we're at it and find our degrees of freedom, which is n minus 1. 10 minus 1 means this is 9 degrees of freedom. And we're going to go ahead and calculate the t-score. The t-score is this data value mean minus the null hypothesis mean over the standard deviation of means. So we were at 30.1 when we're assuming the middle of the distribution is 30 and the standard deviation of the distribution is 1.1, right? So when we make that calculation, we get 0.0909, which means we're 0.0909 standard deviations above the mean. Okay, we're still required to do the sketch here, so let's do the sketch. But this time it's a t distribution, so I'm going to label it as a t distribution of degrees 9, centered at 30. Actually, since we're using a normalized t distribution, it's centered at 0, like a z-score would be, and 1. And then our boundary value is a t-score of 0.09. So just it's pretty close here, 0.0909. And since we're shading to the right, we would shade that. To find this p-value, we're going to use a t-CDF function, like a normal CDF function. And that's going to have us enter the lower bound, which is 0.0909. The upper bound is infinity. And then we can't enter a mean in standard deviation because the only one we can use is 0 and 1. We've already standardized it with finding the test statistic. So that means this is going to end up being degrees of freedom. So we have to specify 9, and we'll label that. This is lower and upper, and this is our degrees of freedom. So in a calculator, if you have a TI 83 or 84, if you go to second and then variables, the same place as normal CDF, see if you scroll past that, there is a inverse T function, a TPDF, and a TCDF. So we'll go to the TCDF function. We can enter 0.0909 for the lower bound, infinity for the upper bound, and we'll enter 9 for degrees of freedom, so it picks the correct T distribution to use. And then that gives me 0.4648. Okay, if you compare it to what we got last time, it's going to be really similar. We got 4638, but that's technically a little wrong because the shape isn't exactly normal. When we did it properly with the t distribution, we got a slightly different p-value. But we will finish it up the same way as we did. Let me just copy this because it's almost the same. So our ending right up here would be with a significance of 0.05, the p-value of 0.4648 is high, so we fail to reject the null. We do not have sufficient statistical evidence to conclude the average speed of cars is greater than 30. All right. So slight differences here. T distribution used, we're required to find what it corresponds to the z-score. We have to find this degrees of freedom thing now, and we have a different way to check the sample size, right? We have to plot some things in the calculator. And then to follow up and do the confidence interval, we would do this. We would say, all right, the confidence interval is going to be the statistic, which is x plus some t star, critical t value, times the standard error of means. So we had 30.1 here. And then we calculated just now that this was 1.1, right? So the question is, how do we find this? So we draw a t-distribution, okay? Degrees of freedom 9, 0 and 1. And if we want 90% confidence, we do the typical calculation, 0.90, 10% left over, 5% here, 5% here. But this t star value is going to be found from an inverse t instead of an inverse norm function. And it works the same way. We can do area to the left, 0.05, because we have that. But just like the normal function, we're not allowed to enter a mean and a standard deviation because we have to be able to enter the degrees of freedom in there, right? So this is the left area. So slightly different things that we enter. If you have a TI-84, you'll have this function, second vars, and then you can go inverse t, right? And then the area will be the area to the left, 0.05, but now you have to enter a degrees of freedom 9. So we get the right shape t distribution. It takes a long time for this to calculate because it's just, there's a lot more going on here. 1.833, okay? All right, and so that means we're going to go 1.833 standard deviations above and below, right? And if I were to calculate that out, we end up getting that the lower bound is 28.08 and the upper bound is 32.12. So the write-up is going to be almost the same as we did in our first guess at what this looks like. There's a slight change in the numbers here. It's 28.1 and 32.1. So a little bit different when we correctly use the t distribution instead of the normal distribution. Okay. And there's one other thing. If you have a TI-83, typically when you go second variables, you will have a TCDF function, but not an inverse t function. So if you're missing the inverse t function, you can use a table actually to find this, or you can just memorize values, but there's a whole set of different values for all different t values. So let me see if I can find really quickly here the t table, because you will be allowed to use this on the tests if you wish. So let me see if I can find a t table real quick. 23 copies t distribution table. Okay, so there is a table. It's in the back of our book, and what it gives is for different degrees of freedom along the side here, there are values here, and this is the probabilities in the tails for one tail and two tail, and the bottom it's the confidence levels. So if we wanted to, we could, instead of doing this inverse t calculation, even if you have a calculator, you can do this because it might be faster. If we're trying to do 90% confidence, you can go 90% confidence and then scroll up in this table until we get to degrees of freedom 9 and get the 1.833 numbered that way. Right, so you're allowed to use a table to find that. Okay. All right, so I believe that's where we're going to stop for the day, and that covers everything we need that we would cover in the lesson. So you should be able to go on and do more problems in the practice packet at this point.